Well, thank you very much, everybody, for being here. I'm going to give a brief review of convolutional segmentation approaches before starting with the graphical segmentation methods that I would like to show here in this presentation. The first one that I would like to mention is the snake. That is a deformation of curves according to the minimization of an energy equation. You see that it stops when it reaches to the boundary of maximum gradient on different variations of intensity. The problem of this algorithm, the original one, is that it doesn't consider the changes in topology. It finishes an envector finds the stops when it reaches to the maximum gradient of it. This is the extension of the snake's level sets. In this case, we represent it in a higher dimensional space. Right? So the deforming contour is considered as a zero level of a higher dimensional function. We are moving to the dimensional function, and we are able to consider the poles and the changes in the topology. Another type of segmentation method is the atlas. The atlas, in the atlas, you represent the structure of your want to segment. For example, here you have the myocardium, the left ventricle, and the right ventricle, right? So it's very simple. The idea is that you have the target image that you want to segment, and you apply the transformations of this structure that you have in the atlas to the input image. And then you apply these transformations, and you have already the segmentation. This is used usually for initializations when you have a more sophisticated. You start with this transformation from here, and you have an initialization of where the final segmentation will be. Another type of segmentation is the Arctic shape models. The Arctic shape models describe objects as a linear combination of eigenvectors around the mean shape. The eigenvectors are the modes of variation of the shape. So, adjusting and picking the target image according to the parameters, we are able to get the final segmentation. And the ones that we want to focus in this presentation that are graphical segmentation. So I started with the classical one that everybody knows. It's a graph. So an image is represented as a graph and can be partitioned into these joints, removing edges connecting the two points. As you can see here, we will go into detail from this type of graph. So let's see the first one, the classical one, the graph cuts. So it's quite simple. You have a matrix that is an image that is represented as a graph. And you have two supernodes, right? You have the descent and the shorts. We will see why it's called the descent. So the idea is to cut this graph in one way that we keep the background connected to the descent and the foreground in the shorts. The other way around, but just to understand the concept. We have several seeds. We put this seed, the user adds this seed here, so this is why we have the weight so thick. And we put another seed for the foreground in red. This is why we have the weight. So the idea is we have to find the minimum cut that partitions into two. That could be these pixels that we don't know, those pixels from here, it could be background, and those pixels that we don't know, that we need to see if it's background or foreground, we will determine that it's for. After cutting this graph. How do we cut this? Let's first understand a little bit. Again, the image is represented as a graph. The pixels are the nodes. So the nodes from here. As you can see in the image, it's very clear. On the edge are the weights indicating similarity. So as we said here is the seed, and we see that the weight is very thick because it's very simple. So this is example. So we have to find and to partition in two disjoint sets, background and foreground. How? Minimizing the cost. How do we minimize the cost? One option is to try all the edges, cut here, cut through here, and here, but this is not optimal. We have to check all the partitions possible in the graph. This is very I'm going to show you. But we have this method from here that it allows, we calculate this minimum cost that we need to calculate the graph cuts in order to find this cost from here. This is called the Bohr-Kessel method. And then this theorem says that we will find a maximum flow between the source and the descent, then we will find the maximum flow, we will have the minimum flow. So we will calculate these edges, right? We will see how it works. I just did a simplification of a graph so that you understand the concept of how to calculate it. The idea is that we need to find all the paths that start from source and it finish in this. Why it's called C? C is when we wash our hand, right? The water is flowing, right? So let's do the analogy. Instead of having a graph, we have pipes. Okay? So we have one pipe that is going from S to A and B. We have to find all the paths that are starting in source and finishing this. Okay, so from this way from here, S, A, and B, what it would be the maximum flow from here, from this one? Well, it cannot be 3, because if we have 3 in this path, this one is okay, we have capacity of 3, this is the capacity, and this is how much, let's say, water we have in the pipe. We have 3, we can fill out this part from this path to 3, okay? But what happens? That is connected A to B, and this one, the maximum capacity is 2. We cannot put, for example, 3 liters of water, because when it goes from A to B, the pipe wouldn't be able to reach the capacity of 3. So we have this analogy of the pipes we see clearly in the next. We initialize all the pipes to 0 because we have 0 capacity at the moment, so, and this is the maximum capacity of the pipe. After initializing that, we will find all the paths from S to D. So let's select one randomly. We don't care about the order, right? So let's go to S to A to B, and B to D. Okay, we have capacity here, maximum capacity 5, but we have the connection between S and A, that is the maximum is 3, and B to D, that the maximum is 3. So the maximum capacity in this path is going to be 3. Okay? But what's going on? That we have 2 empty pipes. This is not optimum at all, right? We have A and D that has 0 water and 0 water, and the capacity is 2. And we cannot fill out more the pipes because they are in the maximum, or they are the maximum at the beginning, or they are in the maximum at the end, right? So we need to find a solution. The solution that Paul Parkinson found is to build a residual graph. Residual graph, what it allows is, okay, I use here 3 liters of water, but if I want to find another path, I can also go in and add an edge here to push back the water where it was before to recover the capacity that we had before in the pipe. So making these paths and pushing back the water back again where it was originally, we are able to find the paths that we were not able to reach before because the pipes, they were empty, because those ones they were already. So in that we are creating new alternatives to fill out the water, pushing the water that we already pushed back, and recovering the capacity from it. So this is the idea of Ford-Furquesson method. Let's see here. So as we are putting the water here, in this example from here, the stream that we use to fill up this part of the pipe, they can be pushed back. So this is what it means. It is edge from here, from this way. The same here, we put 3 liters of water in this part of the pipe, but it can be pushed back and to recover the capacity. So this is what we have. Now that we have these edges in this direction, in the opposite direction, in this case we can continue, the method stop, and now yes, we can continue to find new paths from S to D. So we can go to S to B, B and A and D, right? Yeah, we change it here. You see, because we build the residual graph. The residual graph, what it does is, here, if the Ford-Furquesson thing was just systematic that it's only filling the maximum, we couldn't fill more. You see, that is not optimal, because if I fill water here, it explodes this part. And then, because the maximum of the first part of the path is already done. The capacity is 3, and we put 3 liters of water. So this is not optimal because we cannot add more water in this scheme that we have empty pipes. So this is why Ford-Furquesson decided to incorporate the residual graph. That what it's saying is, okay, if I put here 3 liters of water, let's find another path, and that we put this water back again where it was to recover the capacity. This is what it means, this edge from here. So this edge, it allows to reverse what we did before to be able to find new paths. Otherwise, we'll get stuck here. We only have, you see, one way, and we need all the paths. Okay, so it's one way to restore what we did. Okay, we'll put water here, but it's not optimal. Let's push back the water where it was before, and now we have the capacity that we had in the previous. Yes, this is why we put. We put the water and we put it back. So we get the space at the end of the day. So This is what we did here, so now we find a new path, as we have the new edges that are pushing back the water to recover the capacity that we had before. Now we have from S to B, you can have a path, from B to A, another path, and A to B. So you could make SP, AT. The maximum, again, we have here 3, but at the path, the maximum capacity is 2, we have 2. So then we have now this space, this pipe already full, because we put 2 liters of water and we have capacity of 2. We put 2 here, although the maximum here is 3, because we're going to put more water because we have this is from here and this is from here, and then we put 2. So the maximum capacity, we reach it here and we reach it. So we update the flow. The flow up here is 2 over 2, so capacity 2, and we have 2 liters of water. From here we have a capacity of 5, and we have 1 liter of water, because 3 minus 2, it would be 1. So we have 1 liter of water, and from here we have it full. Okay? So we can see that now we cannot put more water on this scheme, right? But we see that it's more optimal than the first one, that we had the big pipes. Now we have all the pipes full. Even here we cannot really, but anyway, we have all the pipes. We anyway update the residual graph, again, although we cannot continue filling water, but we will consider it because we want to calculate, now we are in the stage that we can calculate the minimum cap. Okay? So we do the same, we push back, if we put water here, we want to reverse that. In that case, we could find another way, in this case, not, but it could be if it was a larger graph. So I will have now to reverse this one that we put the water to put it in the other side, and we do the same. If we put 2 liters of water here, we reverse it in case that we could find another way or another path, and we have capacity 0, and we do that with the new ways that we want. But we can finish it. How we know the mean cap? The mean cap is the maximum flow that we find. The maximum flow, how we can determine it? It's the maximum outgoing flow from the node P. So the outgoing arrows from node P is this arrow from here and this arrow from here. 3 plus 2. Right? And how do you know that you make the calculations? Because it's the same of calculating the inwards, the arrows inwards to the source. 3 plus 2, 5. So you know it's correct because they are going from the D and then going from the S must be equal. Right? But with one, you have enough to calculate the mean cap. So to calculate the mean cap, very easily, we will go to the last flow graph. So it would be this one from here, 2 plus 1 plus 2. That is the mean cap that we detected using the outgoing flow from 3 or the ingoing flow from S. That it should be the same. So it could be this cut from here, and this is as we want to cut the forward, for example, with S, and the background with P, you see that it satisfies. So it would be the final partition that it would give you for the graph. But let's see what problem you can find here. Maybe you can get this. What happens if we are only checking the minimum cap? It can be that maybe the desired hat, it will be this one from here. But as we are already looking the edges, we can find a minimum edge here, and it can give you, it can be biased toward producing a small hole. Okay? You can see an example. This is more clear. This is the typical that you find in every presentation, but maybe this is more clear. Imagine that the edge from here is 1, and this is 3. As I said, the other method is a simplification of trying all the possible cuts of edges. But what would you select? You would select this one, right? Because it's smaller than the addition of these 3 edges. So this is the big problem of random cuts. This is where the next method takes place. The normalized cuts solves the issue that we found in the normalized cuts is a graph-based segmentation method with this systematic global energy minimization, robust initialization, and no sensor required. And it also has a limited number of factors, so it has many advantages, but it has a very main limitation. It's difficult to incorporate the shape package. Usually, when we have segmentation, we need the shape value in the height, not only in the intensities, because sometimes the intensities are not normalized. So we need something else. So to change, to incorporate the prior, we need to change the formulation. This is hard. We will see. So again, the same idea. The nodes are the boxes or pixels of the image. So this is the pixels of the image. The weights again are the similarity between the nodes. But now we had before that we care about the minimum cut, right? Now we care about the minimum cut, but we will also consider the size of the regions. So we will have a balance between cost of the boundary, between minimum cut, but also consider the size of the region. How do we do that? So in the formulation, apart from the mean cut, we will have this term from here, the association A and B. That are the total weights of the edges connecting nodes with me. So it would be the sum of the edges of A in association A and B, and in B, in the case of the association B and B, it could be the sum of the edges. So now it would be a balance of both. So now we won't have the problem anymore. I won't go into details into the formulations because you have a very nice demonstration in Shemali to develop this method of segmentation. You can go to this paper and you will see the demonstration in a very clear way. But I want you to understand the formula, this formula from here, and there is the formula in this formula from here, and finally what you do is to solve eigensystem generalization. So what you will find is, right? So this is it. You have, as I said, the demonstration very clearly in this. It was the authors who developed this method. Let's see how to calculate. So I'm a computer engineer, I'm always going in that direction. I know mathematicians are going more in formula than me, I'm going more in algorithms, so you can develop. When you finish today, you can go and develop your own method. So it's very simple. So we calculate first affinity map, that is giving us the similarity between the vector boxes. So first we have the image M by M, and we need to scan the image from left to right, up and down. So we have a very huge affinity matrix here. For every pixel, you have all the pixels from here. You say, wow, this is very time consuming. No, well, memory consuming. No, it's not the case because you're not going to check or you're not going to have a value for each pixel. Wait, sorry, what's the value? Well, it's the next slide. Yeah, I just want you to understand that you can see that maybe it's a very cute affinity matrix, but you won't have a value from every pixel with every pixel because you have a neighborhood around, right? We have a radius. So we'll check maybe 16 or 8, or depending on from the current pixel. For example, node 0, you will have only 16 values if you want the radius between the 16 from this current pixel. You won't have very few matrix because now it's invisible in memory, right? So we'll have a sparse matrix. This is what I want you to understand from this one. Now we calculate the weights. But the weights, I put it in a very simple way. So what we do is very simple. The exponential minus the norm of the differences of intensity multiplied by the exponential. So what would be the same of the product of distances of spatial and intensity values. So it's very simple. Very simple. What you consider is that the intensity differences, intensity differences and the spatial location from one pixel to the other. In the paper, you will see it's exponential minus the norm, the differences between intensities from the current pixel to the new. Also consider multiplied by the spatial location. So then we have the diagonal matrix that, as I said, you have one node here, node 0, and here you will have the similarities of the neighbors, right? So what you do is to add every row and to put it into the diagonal, right? So we will have from the diagonal all the information you have from all the neighbor pixels, and you will put it all in the diagonal. So you will only add. Okay? We'll add the weight matrix and put it here in that. So making that, we will do the diagonal matrix subtracted by the weight matrix, and we will have a Laplacian matrix. And we will calculate how compute the eigenvector decomposition. Here you have an example. This is what I did from paper that you can also read here in it. What I did here, it was to calculate. Here is the eigenvector with the second smallest eigenvalue. As you can see, I threshold it. I reshape it first because it was a 1D vector. I reshape it as an image and I threshold it. So this is the final result of applying this equation, this algorithm. Okay. So it's very easy to implement. You have also the code there, Shemali, offer you those too. So let's see some examples that are using this method. As I said, the original method doesn't have shift priors. We need to reformulate, and this is what I did for my thesis. So I incorporated the shift prior, and what I had in the solution, so some examples of results that I got with this method, changing the formulation, were quite good. So you see, 25 cardiac MRI images, one were here, and we wanted to cement the myocardium. And you can see that it's quite challenging because we have here the papillary muscles and the laboratory that has a lot of immunogenities, maybe with the lives and secretary, but at home we will see. So the results, they were really nice because we were able to deal with the papillary muscles and some with the immunogenities, and the results were very critical ones. Also in the high contraction, that is more difficult to cement because the shape is slightly forming quite a lot. Even like this, the results were very good. And in the relaxation at first frames, they are also very challenging. The results were very good. So now let's move to another method. As I said, the other one, it's a pain to incorporate the shift value. It was my thesis and it was really a pain. So random was proposed, well, it was proposed for other topics before, but for the segmentation, it was designed by Leo Grady. So we need to thank a lot to Leo Grady because he also incorporated a prior term that it makes very easy our lives when we want to incorporate shift prior for additional information. But let's see now first the concept, right? First we'll go to the concept of random walks because, as I said, it was not Leo Grady to invent the concept, but yes, he adapted for the segmentation. Let's see. So the random walks is a graph-based segmentation method. It's a good candidate due to its numerous advantages, its robust noise, its robust indicators, and we don't have the drawbacks of the main graph that I showed you before. We have to show you the concept is little animal. I don't know if it's an ant or what. It doesn't matter. It's great. And we're going to see the destiny of this little animal. Let's say this. He will just fall off of the cliff of doom, or he will go to the peak of disaster. We see that the fate of this poor animal is not going to be very nice, but I don't want to go into facts. Let's see. So what random walks does is to represent the segmentation in a probability distribution. So in this stage, this animal is taken. What options he has? He has the option to go to the right or to go to the left. In this case, as it's a simple example to show you the concept, we have 50% to go to one side, and 50% to go to the other. So if he falls to the cliff of the doom, the probability that he has to fall is like 1.5. We go down 1.5 and 1.5. So we will multiply this one by this one. This is why you have 1A. Okay, or you have also this option from here and from here and from here as well. So you have all the options that you have. You have 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, and 1.5. You can see multiplying concatenating the probabilities. This is what you have to do. You do all the combinations, you will have the poor little animal to fall off the cliff of the doom, it's 2 thirds. What is the other probability? That he goes to the pit of disaster. So again, the same idea. If he goes to the pit of disaster, you have this probability here, so you will move to here, you will move to here. Yes, this is why you have 1 here, or you will go move to here, to here, to here, to here. This is why you have 1 divided by 16, and all the options that you have here, that is 1. So you see that this poor little animal won't have any nice or any positive destiny, or will go with 2 thirds to the cliff of doom, or 1 third to the peak of the sun. So he's playing from 2 events, like 2 boundaries, and he's like calculating the probabilities. Now, get this idea, but now for the segmentation. Now the segmentation to go to one path, to go to one step to another is not going to be 1.5, as you can see. What is going to be? Well, it's going to reflect the image properties, because we will have, for example, the variations of intensity. So to go from one pixel to another, it can be very easy or very hard according to the image. So this is the we have a very simple example of half and half, and in that case we will consider to go to one step to another according to the image. The idea is exactly the same. So as I said, random walks propose first an initial segmentation method and clinical extension. We're going to talk first of the standard one, the first one. So we put 2 seeds, so the user asks 2 seeds, 1 red and 1 blue. 6 for background and foreground, okay, also the same. And then imagine that this pixel is already labeled because I already did the calculation. But imagine it's not calculated, so it's white. It's a label. So it's a label. So what we do is to calculate the probability of this little man goes first to the blue one than the red one. So what we have to do is to calculate the probability to go to the red one and the probability to reach the blue, see? And then we will get the maximum. So the maximum probability is assigned to the underworld pixel. So if we have more probability to reach first the blue one, we will assign the blue label. If we have more probability to reach the red one, see, we will assign the red label, right? Understand? So we calculate the probability one C to another, and we get the probability to reach first one or not. Similar to the example that we saw before, we will use the number. In this case, to move to one step or another step, we will have half and a half, you know, we'll have the probabilities according to the image. Okay? So that here is exactly the same also. So to make it easier, we assign each pixel to the label for which it's most likely to reach first. Here we have the 6, and again the same concept. It's repeating all the time, that is all the time repeating on the graph segmentation. These are the nodes, this is called no similarity based on image features that are the weight, and the small weights indicate the similarity with things. Partitions a graph according to the nodes. This is the same idea, but the difference comes in how we calculate. So every method uses a different type of calculation. And this is very interesting because we have this station from here. This is what I mentioned before. Leo Grady did a great job because he extended the original random walks, the law for segmentation, and he incorporated an energy term for the shape. So this is also from another work that they did. You can find the paper here. And I have an image, and I built a prior, an initial prior. As I said, you can use other methods to have a prior that is close to the solution, but it's not the final solution. In this case, I use an analog-based segmentation method to have an initialization of my prior. Okay? So from that, what I did is to calculate the Gaussian mixture model from the image. So I just use the histogram and I match it to the Gaussians, and then I had something. I had the shape prior in here, that is the points that are close to the shape prior, they have more priority to belong to the shape that you want to cement. In this case, we are cementing the cochlea. And then we also built a confidence map, because we are close to the shape prior, but we are also close to an edge. It means that we are in the correct position of the cochlea. So I combine the confidence map, my shape prior, and the Gaussian measurement model. I combine it into one, making this probability map. So this probability map from here incorporated into the original random walks, and I was able to segment very well the. So this is my results from this paper right here. This is the segmentation in 3D. This is my segmentation, results of my segmentation, and this is the ground truth. You can see it's quite accurate. It's very, very simple. So now let's go into the test, because most of the people are interested in deep learning, but I wanted to make some references to the other methods that we don't have to forget. And let's see what words we can find in deep learning using graph-based segmentation. Here, I didn't talk about graph search because it's something very basic, and most of you are mathematicians, no? Deep graph and paths. It's not something that I must to get much in detail. But most of the words that I found in the learning graphs is with using graph search. So in this word from here, play on fun, what they do is to apply first a deep learning method that they obtain a probability map. And from this probability map, they apply graph search, like even more sophisticated, like fast marching, to find the final segmentation represented into polar. You have a probability map that can be going in this way, but you don't have a final segmentation. And finally, with a search of minimum path, you are able to determine the final segmentation. You find a lot of papers like this, very, very similar, using different methods, but in that Now, I found another category that is deep learning and random walks. That you can see it's very similar to my work that I showed you before. You remember I did a probability map, and then I introduced it into the random walks formulation. So this work is more or less like I did, but instead of getting the probability map, where I use Gaussian mixing model and the original image, the shape right, also I use the confidence map. They use a deep learning method. They obtain this probabilistic map. The seeds are automatically obtained using also the regions and the confidence map and the regions level. So in here you are able to obtain the random walks obtained from the deep learning instead of using the simple methods that I used. So the results were very nice. Here you have the deep learning, here you have the ground truth and the original image. And well, you can see that with the random walk, which is the one that we are interested in using deep learning methods, we are able to recover, for example, this one is very changing, this bicycle from here, and you are able to recover it very well. So this is really interesting that maybe you can combine, instead of using only deep learning or using only graph-based segmentation method, why don't combine them together, no? You get the power from one and the power from one. Let's combine it together. But then there is the third category that I wanted to mention, this type of course of graphs and neural networks. It could be the graph convolutional network. So now that the computers are like evolving and the technology, is increasing and very powerful now, these words are starting emerging a lot. So well, the idea is that instead of having an image that you introduce into the learning or to have figures and fit the deep learning methods, we will have a representation of a graph. We'll see how later. So we will have the graph, and in the combination layers, what we'll have is to represent the features, but not from an image, not from layers of graphs, right? So we will learn the graphs and the weights of this graph. We'll see how, because we will see the formulation. In that case, we will see the formulation is very easy. But first, let's go a little bit more in detail with graph convolutional methods. So, as I mentioned, before we had, for example, in convolutional neural networks that we'll see in detail now, a regular structure where you have a global neighbor and you have the global pixel and you have the neighbors around. But now we don't have this information here, we have a graph. But we need one way to determine what are the neighborhood from this pixel. This is why we use the adjacency matrix that enable the model to learn the figures from the neighborhood. So having this figure, we go to the first introduction the deep learning. Because I'm going to, as this presentation is for everybody, I want also to introduce this concept for the people that want to know more about deep learning. It's very interesting that you can go to this web page and you can play with the parameters and see how deep learning works. So, shoot the slides introductory of deep learning. In this web page, you can play with the deep learning parameters. Also, you have different inputs. You can play with the figures. In this case, it's the vertical position and the horizontal position. And you can see the weights, how they are, the weights affecting the neurons until you get the final classification. You can change also the learning rate, the activation, the randomization, and noise, and see, you can see clearly when you need more figures, when you need to add more hidden layers, because in this case it's very simple, it's separable. But you can see that in some cases we need to add more layers, and we need to add also more layers, and you can play a little bit. Using this web page from here, you don't need to install anything until understand the concept. You can see here in the initial we need 2 features, it was not really accurate the classification, but adding these more features from calculations made from these 2. We have a better classification. You have this web page to play in case that you want to get introduced into learning, you are an expert in slides. But I want you to focus on these 4 parameters from here, the ones that we saw. The learning rate, that controls how much change the model is processed and making error described weights are rotated, so how the speed that we are going to learn or the model is going to learn. And it has to be, you need to check this what the value will happen. Because if you have a very good value, as you have the learning has a pretty decent scheme, if you have a very good value, a very big value, what you have is an oscillator. You oscillate here the final solution, so if you want to reach the minimum box, the solution will go here, then here, and here, and you will reach the minimum box. Be the minimum level. So if you have a learning rate that is very small, what you will do, you will reach very slowly to the solution. So what you need to do is to have a learning rate that it's like at the beginning, to have an optimizer, no? At the beginning, to have it very big, and when you are reaching to the solution, then to become smaller. You have a lot of optimizers that they do that, and they can do it automatically. Then we have the epochs, that is the number of times that the learning algorithm will work through the entire feeding size. If we have many epochs, you can suffer overfeeding, but you have very few, and you can learn. So, as I said, you can be very expert, but every data set is a different one, and you need to try and remember many times. Also, the batch size is very important, so divide the training data and devices to pass it to the network. That's our memory, is limited that we can control the information in memory. But this character, like the other one, this one is not affecting the work accuracy at all. And another one that I want to mention is the activation function that provides forward to the next layer of the deep learning. So now let's go. Now you have an overview of what the learning is not working. We will go to determine the convolutional error. The convolutional error network, you have several filters that when you want to extract these filters. Like, for example, the edges, the curvatures, also something more sophisticated. So you have the convolution that you extract those filters, and the pooling, what you do is that you have plenty of information, you synthesize this information that comes from the convolution. So you have those samples with that information. And then what you do is to concatenate convolutions and poolings that start in different levels of abstractions of the filters. For example, you can see, imagine that we have 3 convolutional layers, and this one represents this low-level filters. You are extracting edges, you are extracting curvatures, you are extracting low-level structure of the image. In this case, for detection of patterns. Then we can have another convolution in this stage that we have a medium level. Let's say that we have here an eye, a nose, so we have a medium level of extraction, right? And imagine that we have another group of here convolution and pooling, this cycle here. Then we have something in a high level. Like, for example, eyes here, the nose and the mouth, because we cannot have the mouth, right? So the structure has to be a face like. So this is why we are concatenating like the different convolution layers. We are extracting in different abstractions of the features in different levels. Well, if you want to know more details, you can have here the classifications of max. That is expecting a one vector, is here you need to plan and it's very simple. For finishing to understand, we will do it with an example. Of course, I did 1D because 1D is easier to understand, but it's the same in 2D or 3D. So in that case, we see the example of convolutional neural network. We have the filter, as I said, it would be like the filter operating the edges, some areas of the image, and you're gonna use it in the whole input filter. So you use it first to this tree, then to this tree, then to this tree. The example is started in this level, but it could be all column. So what you do is to apply the Windows filter, that would be some of the edges, to do the dot product from this input spectrum to the filter, 9 multiplied by 1, so plus 0 minus 4, it would be 5. So you can see here. And then you apply the activation, that is to propagate to the next layer. And in this case, we use the ring that is the one that is most used. That if it's bigger or equal to 0 or bigger, you just the output is the same as the input, otherwise it's 0, right? So here you have negative value, so you have 0. You let this value to pass because it's bigger than 0, 5, 0, 3. That's it. The home can understand. And finally, we contain some information because we have plenty of information. We do not something synthesizing of the data that we've been from the community after the activation. So we do a max, we can do an average, we can do a max. So what they do is you have in this case Windows 2 by 1 filter. So we control this, we will check this, we will check this with the maximum of each. Why we have separated the shift to 2? Because we have a cycle 2. If we have an extractor of 1, we will do this, and this, and this, but as we have an extractor of 2, we switch 2 pixels up. So this is what we do 0, 1, maximum 1, 5, 0, maximum 5, and 3, 0, maximum. So you bring the final process that an example of the convolutional learning. Why did I explain to you that? Because I wanted to have clear, because maybe I put you this slide only and you don't know how it works. So I prefer you to understand on the introduction of why the reason of this slide, because we are going to change the transformation, the formulation of the deep learning in the graph convolutional. In this case, in fast approximate spectrum. There are many methods that do that. But I selected this one because it's quite simple. I think it's really easy to understand. So here you have the scheme again. Before we didn't see the bias because we usually omit the bias because we see that it's always there instead in the output. So I see it's always there, sometimes you don't see it, but it's always there and we can. So the formulation for the forward pass of neural network is the waves multiplied by the representation plus this one. And then you apply the calculation as you saw in the example of what's very simple. So what we do in the graph convolution. The graph convolution, I said, the neighbors, we don't have this information directly in the graph. But we need this adjacency matrix. This is why we have this transformation from here is transforming to the deviation from the weight multiplied by the filter representation multiplied by the density matrix. The density matrix that is giving us who are the neighbors, right? But we will consider also the self loop. How we consider the self loop? Adding the identity to the adjacency matrix. What does it mean? That in the adjacency matrix we will obtain the average information of the neighbors, but we also want information from itself, right? From the pixel. So this is why we have the set loop. We are in the adjacency matrix the identity to have the figures to from the current pixels. So this is the reason that we have this A added in have the figures from the current pixels apart from the neighbors. So we normalize, because we also need to normalize, so this is why we have this normalization, that this is the degree matrix, that is going to be the degree from this matrix from here, just including the identity, this is why we have the hat here, and the rest of the parameters that are. So this is the way that we can incorporate the graphs into the deep learning. This is one way. There are many. In literature, we can many. So now, finish. I would like to summarize the benefits and the drawbacks of this method. The use of graph-based segmentation methods. We don't need a large number of samples. We have to learn the method. You can just simply use it and that's it. So this is a real advantage because usually the hospitals you don't have many data. So this is a really good advantage. Also, well, as a disadvantage, the incorporation of the priors required to the formulation. Even random walks, you don't need it because the author already did it before. Usually, but requires this change of formulation. But the representation of the image is sparse, so we don't need a lot of memory of the system. You can need a lot of memory in order to run this type of methods, but it's not true because you are using only a label book, a radius around the current pixel. You're not using all the pixels with all the pixels. If you can see there are advantages and disadvantages of this method. The deep learning method, well, you need a number of data sets to be able to learn the questions to learn now. So you need to have data sets available. You go to the hospital and you don't have that. Yeah, and as advantage, yes, the deep learning methods is straightforward. Like I say, you have these parameters you can play with. And they agree, this is a thing where the future should go. It's a combination of information obtained by the graphs of the deep learning. You are already obtaining information before starting the training, right? So we can combine the information from the graphs and also the deep learning techniques, and even before starting with the deep learning, we already have information obtained by the graphs. So this is really interesting. That we think we can explore this to make it hybrids like deep learning presentation. And something I would like to discuss today, if we have time, is like, what do you think about this method? Because the method will move in the future because now the knowledge is like evolving, like more powerful. No? Those methods they will be also incorporated in the new deep learning method, so it will be left behind. It could be a big leap because we saw that we have a very nice results combining both. So as I said, they can give you more information even before starting. So Thank you very much for your attention. I hope it was not too much in our presentation. We wanted to give you an overview of composition information to understand all the process together and see if we can see how to continue, this kind of work that is now emerging, research now. Yeah, you have 1 minute.
Now, volume of the report cloud, and I'm watching the tradition now is to imagine domain, cloud, and there are other people who are studying the pieces of trees, so definitely going to find GCNs here, and I mean even they create new type of evolutions, like in the 2D domain, the imaging with the image to the content, features, your basic method is called the point clouds, because we have this unordered set of points. They create evolutions or full connected entities, like we already know, and they make them in space, mimicking actually 3D evolution. So imagine that creating neighborhoods of points, creating a kernel outside of space, and this element-wise multiplications. They create this convolution, but they don't use it. But indeed, all structures are convolutional based because they use this mind of they have the output features from the kernels. So now they are doing also the same with the DCS. So definitely they are going to stay there.
I would like to see a presentation of it. You want to have AI. Very interesting. Very interesting line of research. Thank you.
I'm not working on graphs. I'm studying them a little bit now, but I really want to work there. Yeah, sure.
I'd also like to thank you for your talk. I really enjoyed it. I thought you did very good. So I have a question that was like this. It looks like from the work that if you're able to incorporate the fires, you get better results. There's only some in your segmentation.
Yes.
So since you say you want to kind of find out how to combine the old and new, so how can you incorporate fires with the structure of the program? It says you use convolution and you already design variables. So is there a way that you can all this training stuff is always fully connected? Everybody's going to lots of training. Usually be way more efficient if you say we're going to copy it.
Yeah, well, there was some kind of prior information, like using, for example, watersheds that they know the division and make those watersheds they put graphs and then they represent it in the learning methods, like certain information that you need. This is why I wanted to make an overview of the segmentations, because you don't use one. Maybe you can apply one of those that I proposed at the very beginning, for watershed and then training. But what they do is to separate an image into pixels that have certain similarities. And you can get, instead of having one pixel, having this case of one pixel, you have these regions that they have certain similarities represented in a graph and then to apply the deep learning. There are things like that, but of course we need to study a little bit more how to perform that. Yeah. This is why I felt very interesting this topic because some way to do it, right? I think it's something like that, or they want them presented like instead of having manuscript or whatever. So this is not to be in the level of the pixel, is not groups that they share certain density or certain figures, or maybe you prepare it prior, like before, and you say, okay, this group they tend to be the same. So give a probability instead of giving the same 0 or 1. So maybe with the different alerts as an important. It's not that still we have to make a lot of research on that. It's really a good question. I think we should think about it. You need a lot of data to learn that, but we don't have it usually, and
it's really expensive.
And it's very expensive. And with those methods, you don't need it. You don't need the online, you need maybe 10 data sets. I think I use 10 data sets. It was more easy. 10 data sets for all. And this is where
you do.
Yeah. So I think it's an option that now is like everybody is like forgetting. Oh, I need this the thing I have when I go to a conference, natural learning, still learning. But what about the other methods? We don't have thousands of data sets available. This is a product fine. Now I have 100 of that, 100 of this. So let's know that we have these options. We have a lot of methods here. I didn't use only one. I used using the prior. In one I use Harlan stage model. Another one I use Artificial model. The one I show you with the PCAs and the most variation. So we have a lot of alternatives.
In fact, now we've got a lot of data, and to label this data, it's to train neural networks or train neural networks that are able to generalize in every condition across the domain and whatever. What are they doing is few-shot learning or zero-shot learning. It's like techniques that you label, let's imagine a frame of video, frames of data from video or whatever. You label the first frame, and the network is able to learn from all the frames. Or you go to fully unsupervised learning, the network to learn primitives of this 3D data. So it's actually the network to learn